Global workflows have transitioned toward an environment defined by real-time data and interconnected systems. This new baseline for the 2026 economy is known as the simulation age. The majority of major industrial infrastructure projects now rely completely on parallel virtual pipelines. In 2024 and 2025, over 70% of these projects utilized digital twins for pre-visualization prior to any physical construction. Operating within these pipelines requires a mastery of spatial logic to interface with complex AI systems and large graphical models. Professional success is increasingly tied to this system-centric model, where variables are updated and visualized in real time. The interactive, multivariable 3D simulation has become the primary language of human-AI interface and professional collaboration. Despite these shifts in the workforce, traditional education remains tethered to a logocentric model. This framework measures human intelligence primarily through the linear consumption and production of written text. We are currently forcing students to navigate simultaneous, non-linear realities using sequential single-file tools. Brigita Biondic's white paper proposes that visual literacy be treated as a foundational cognitive requirement across all academic disciplines. The proposed institutional solution is Iterative System Modeling, or ISM, a pedagogy that demands students demonstrate mastery by manipulating complex visual data. An education system that continues to reward only the static paragraph produces graduates who lack the literacy required for real-time problem-solving. According to Pivio's dual coding theory, the human brain processes verbal and spatial information through two distinct neural channels. When a student attempts to learn a highly interconnected concept like climate change through text alone, the linear verbal channel faces an immediate bottleneck. This results in a translation tax, a massive spike in extraneous cognitive load caused by forcing multivariable systems through a single-file verbal pathway. Mapping these variables spatially clears the bottleneck, allowing for an intuitive understanding of the relationships between data points. Relying strictly on text for systems-level education biologically handicaps the learner's cognitive bandwidth. This spatial approach also transforms how students produce work, shifting from static drafting to active simulation. Traditional writing is a slow-loop process, where the delay between a student's output and a professor's feedback can span days or weeks. In a real-time engine, adjusting a variable like lighting or physics provides instantaneous visual feedback. This high-frequency iteration aligns with the flow state, where immediate feedback loops maximize engagement and knowledge retention. High-frequency visual feedback accelerates the speed of learning by allowing for dozens of correction cycles in the time it takes to produce a single rough draft. This pedagogy introduces spatial argumentation, where the traditional static thesis is supplemented by a navigable 3D model. In a traditional history course, a student might write a paper listing several reasons why the Roman Empire fell. Under the ISM framework, that same student builds an interactive 3D map where users can manipulate variables to prove a historical thesis. By maxing out sliders for inflation or barbarian incursions, the user witnesses the systemic collapse of trade routes and borders in real time. This forces the student to demonstrate an understanding of the active, systemic relationships between historical pressures. Grading these complex, real-time simulations requires a shift in how we evaluate student work. The Iterative System Modeling rubric measures systemic logic by how effectively a student identifies the relationships between multiple variables. This rubric prioritizes product as process, moving the focus away from the final polished render. The most accurate map of a student's cognition is their version history, the sequence of pivots and failures leading to the final model. The rubric also evaluates AI collaboration, rewarding the use of AI as a rapid coprocessor for system prototyping. By assessing the versioned logic, educators can rigorously grade problem-solving processes that AI cannot simulate on its own. To confirm true mastery of a system, instructors can employ the break test. During a live assessment, the instructor introduces a sudden chaos variable, such as a localized fuel shortage, directly into the student's balanced model. The student's grade is determined by how quickly and logically they adapt the architecture of the system to accommodate this new reality. Rote memorization provides no advantage in this high-pressure spatial environment. The break test ensures academic integrity by evaluating live, adaptive systems literacy. Shifting institutional standards to accommodate this new literacy must occur in distinct phases. The roadmap begins with Phase 1 visual synthesis assignments, moves to Phase 2 real-time lab defenses, and concludes with Phase 3 full integration across the curriculum. This leads to the ultimate goal, node-based literacy, where mapping complex logic is taught with the same academic rigor as traditional grammar. Institutions that refuse to evolve past the paragraph will fail to prepare their students for a world that operates in real time. The replatforming of education to meet the demands of the simulation age must begin now.